right, let's look at number 15. So they give us this graph, and I'm just going to kind of generally sketch it. I'm not going to get real detailed on it. The graph does something like this. It goes up to 4, and it goes from -4 to 4. This is so easy, it doesn't seem like it should be calculus. The function was the f of x equal 4 minus the square root, the absolute value of x. So this is our absolute value parent function, which looks like this, and the negative flips it. Okay, so now it would be down here, and then it's scooted up 4, 1, 2, 3, 4, and it ends up like that one on the top that you see in the book. So they just graph that function, and they say set up a definite integral that yields the area of the region. Do not evaluate the integral. Okay. All right, so if we think about, first of all, wouldn't this be really easy to get the value of? Because it's just a triangle. It's got a base of 8 and a height of 4. 1/2 base times height would be half of 8 times 4. Half of 32 is 16. Well, we were told not to do that. But we could see this is the area under the quote-unquote curve here. It's just a weird, it's just this absolute value function. So if we want to set up a integral to do this, and we definitely don't want to have to go in to do this because we don't even know how to do the absolute value integral yet, it would be 4, okay, it's the function, and then the change of x, because remember the function gives us the height. The width comes from the dx part when we look at this definition here, and then we're just going to go from -4 to 4. And that's all we're doing there. Forward, you just write the integral down. You write the two values that you're looking between -4 and 4 are where my region starts and my region ends. Putting the function down here and then just putting dx because we're integrating with respect to x. And because over here we defined an integral as letting the number of rectangles go to infinity, dx ends up being kind of it ends up just being something that tells us we're integrating with respect to x, but over here it was literally making the rectangles infinitely small. Now we've been talking about these Riemann sums is how we got into this. It went from a Riemann sum to a limit of a sum to an integral. And that's how they actually came up with all this stuff. You don't just find area under the curves with a Riemann sum, and as a matter of fact, that's why these things are named after the Riemann. It's got like 4 names. I wrote it down on my George. What's his name? George Friedrich Bernhard Riemann. He got credit for this. He didn't develop it, but he got credit for this because he actually extended the application of it from just being area under a curve. He extended it to find arc lengths, average values, centroids, volumes, work, and surface area. So he actually showed that you could use this for more than just area under a curve. So that's why he got it named after him. He didn't really develop it. He just extended the application of it. So 21, they tell us g of y is equal to y cubed. And look at where they put the area here. It's not shaded in underneath the curve, is it? Here's the curve. It goes up to 2, and it's like they went across here, and they shaded in this right here. So it's kind of the area above the curve bounded by the horizontal line y equal 2. So what you do here is instead of looking at your x's, isn't that kind of going along more your y-axis? So they give you the big hint, they put the y cubed there, okay? But you integrate it from, since you're looking at the y-axis instead of the x-axis, you're going from 0 to 2. So you just do this, and you put dy on it because we're integrating with respect to y instead of x. So there's the first time we really see the different variable in there. So I can do things like that, and we'd use the same integration rules. It's just that we're integrating with respect to y to find the area between the curve and the line y equal 2. So that's one different one. It's the only one like that in there. I would not put that on the test. It's kind of the unusual one of the bunch. So you just take the function, stick it in, the dx in most cases, and then just put your n values here. Normally it's the x's that we look at, though. We're going to sketch the region whose area is given by this integral. So if you think about it, isn't this a line with a y-intercept of 5, because this is y equal mx plus b. Remember all that line stuff that we reviewed at the beginning of pre-cal that you learned in Algebra 1 and you reviewed again in Algebra 2. It's got a y-intercept of 5, 1, 2, 3, 4, 5. And the line has a slope of up 2 over 1. So I'm going to, hopefully you've got some graph paper or you can use something. I'm just going to kind of, because the iPad's going to run out of room, I'm going to just go ahead and do that. If I had it going from 0 to 2, that means that I need to extend that line on out. And if this is 0, 1, 2, if I want to know what area am I trying to find there, it's the area bounded by the y-axis, the x-axis, the function y equal 2x plus 5 that I graphed in orange, and then the vertical line x equal 2. If I were to, this is a very rough sketch, but this is kind of what they're asking you to do here. I did 29 and 31 on the video, but if you look at those, just if you're looking in your book, 29 is another one of those absolute value functions, kind of like number 15 that we looked at. And 31 is a half of a circle. If you look at what they've got there, x squared, you have to think y equal square root of 9, just briefly, in case you don't want to go watch the video. You have to kind of, on 29, translate it over here and think if I squared both sides, I'd end up with y squared is 9 minus x squared. And if I move the x squared to the other side, isn't this what the equation of a circle looks like? X squared plus y squared is 9. So what this is, it's the upper half of a circle going from x is negative 3. So if like negative 3 is down here and 3 is here, we have a radius of 3. So I know I got to go up to 3 here. And this is the upper half of the circle. The reason I know it's not the whole circle, they didn't put plus or minus out in front of it. They just put the square root, so I'm assuming that I'm only working with, bless you, the positive square root. Mine's been going off all day. It's okay. So that's on 29 briefly, that's what they're asking you to do. It looks kind of weird, and if you don't remember what the equation of a circle looks like and think about the fact that they don't give you the y equal, that's kind of what they substituted for f of x, which is equal to y. Does that make sense?
Yeah.
Okay. So there's a video on that one too if you want to watch the whole thing. It's slower, but that's how you're thinking of these. Pretty fast this week. And if you don't understand what to do on something, please feel free to email me and I can shoot you off a video or post it, let you know, hey, I just posted it on CoreSites. 1 and 7 are the weird ones. 1 through 7 are kind of the weird ones. We can always go back to them if we have time, and that way you wouldn't have to listen to the video. Okay, it says evaluate the integral, and here's the integral, using these values. Now, this is weird. I'm not quite, I think they're just trying to get you used to the fact that you can divide an integral up. We have these, they give us these values. If I integrate from 2 to 4, x cubed dx, it's 60. If I integrate from 2 to 4 and I have an x dx, it's 6. And so these are like not given values. And if I have just a dx, it's 2. So these are like things I'm going to use to figure this out. We're not actually going to integrate here. The point of this is this. I can split this integral up because there's a theorem in this section that tells me this, so I'm just kind of going with the application of the theorem here to explain it so you can get through your problems. I can split this up into the integral from 2 to 4 of x dx minus the integral from 2 to 4. Let me put the 8. I can always put a constant out front and then just put the dx here. I could put 8 dx after the integral if I wanted to. But because of the way they made these definitions over here, let me separate them so you can. All right, Notice all of these integrals that define, they go from 2 to 4, right, on the right-hand side. So here's x dx. Let me color code here. Here's x dx. And so x dx from 2 to 4 is 6. You see what they're doing here? Minus 8. Here's the integral right here. Should have circled it in a different color. Here's the integral right here from 2 to 4 dx. That's this one right here, isn't it? So it's 2. So it's 6 minus 8 times 2 is 6 minus 16 is negative 10. Now, areas, when we integrate, it doesn't have to necessarily represent an area. We're talking about area in this. They're using the application of area just to keep it simple. We can have an area be positive, we can have an area be negative, and we can have an area be 0. Oh, this time's running out. If I were going to go from 2 to 2 of whatever function, I'm just going to put in general f of x dx, that's going to be 0, because if I'm starting at 2 and I'm ending at 2, I have no rectangles, right? So you're going to see that some of these problems are going to require you to kind of think about that a little bit. So you can have an area of 0 if you integrate from one number to the same number. You don't really have any area there. I could integrate and get a negative number, and this is where this comes in. What if you had a function, for instance, this might represent cosine, right? Maybe one cycle of cosine. Wouldn't you have as much area above the curve as below the curve?
Yeah.
So I could look at this in parts. Maybe I don't want to come out with it being the total area is 0. Let's say that this is some positive value a, okay? Wouldn't this value over here, if I divide this up, this would be positive a. Over here, it's going to be the same amount because it's a...
Wouldn't that be double?
Yeah, because it's only the half curve on the positive.
Say that again, then what?
On the cosine, it starts halfway, so...
Halfway.
If it were the
The cosine
full-
is going to have
if it was-
equal.
I should have chopped my graph off a little earlier. So let me draw it like that. Let me say I'm going to integrate from,
Moving up suddenly, actually.
that would be 0, let's see, that's pi halves, so this would be pi. What if I integrated from 0 to pi? Is that what we're saying?
Sounds like a full
Okay.
cycle, yeah.
That would be let's put it this way, a full cycle would be
A
it
full
coming
half
back
cycle,
up. But let's
half
talk about
cycle.
area. Let's just look at it as
Half
area,
cycle,
okay?
yeah, okay.
So if I'm looking from here, and let's say I forget all the stuff that's on the other side of the screen line, this would be like some area A, this would be negative A. If I integrated that whole part right here, it would be 0, because this is a positive A, and then we have a negative A. So you can have a negative area. It's usually what's underneath the axis in between the functions. So those could, if I integrated the whole thing, I'd get 0, but that really doesn't tell the whole story, does it? There's some above, some below. So you can have a negative area.